Good afternoon, everyone. Today I have a couple announcements to make regarding our final exam information. So according to the final schedule on our university's website, for this class, we will have a final exam on Tuesday, May 18th. So I'll make it available for the 24 hours duration on that day. And you will have 3 hours, any 3-hour period during that 24 hours to do the final. Okay, final will be cumulative, but mostly with a really heavy emphasis on the content after the second midterm. So you can focus mostly your studying on this after the second midterm. So when we start doing the rotational motion, when we started doing the rotational kinematics. So there is a practice exam that's been uploaded. Make sure that you work it out before you look at the solutions. I will post the solutions later this week, but before I do the solutions, I want you to have an opportunity to try to do it on your own. Okay, so there will be 25 questions total on the final exam, 25 questions, okay? Including multiple choice and some enter the value type of questions, very similar to the midterm, but just a few more questions more than the midterm. Okay, all right. So there are some extra practice questions called multiple choice questions. I uploaded along with the practice final. So if you wanted some more practice, you can look at those. There is a post-assessment. I'm sure you are expecting this. The pre-assessment is the multiple choice test that you have taken at the beginning of the semester. Okay, and again, this is an assessment for the purpose of for us to understand how students are learning, and is not to be graded. So you will not be affected. Your grade will not be affected by how well you did on this assessment. It's now posted on Blackboard, and then the last under weekly materials folder at the very bottom, you will see a link for post-assessment. It's timed for 45 minutes, okay? And you're not gonna be graded as long as you answer those questions. Just try your best, answer your questions. There is no need to Google answers because it's not graded. Will be due at the end of the May 21st. So that's the week after the final. So make sure you have that done before, so I can compile that into your grades. So you get an extra credit for 1 point added to your final grades, as long as you do them honestly. So, okay. Any questions? Any questions about the final and practice exam and stuff like that? We have 2 more topics. For this week, we will do simple harmonic motion. And for next week, we will talk about fluids. Okay, along with universal gravitation, these later chapters have relatively less sort of problem-solving type of questions. Simple harmonic motion, just because you can see the extent of the problems that we solve is not as much as when we did the energy one, when we did the momentum one, when we did the rotational one. Okay, so even though these content, there are a lot of new information, I would think that the question that's being asked are also more straightforward in the sense it's usually a short question instead of a very long, complicated problem. So hopefully that you'll stick with us till the end of the semester. Just 2 more weeks to go, okay? All right, so today we will begin a new discussion that's called simple harmonic motion. This is actually a very widely used model in physics. So when we say in physics, we build models, right? From the beginning, you have a point particle model. When you can use something as a point, you don't really care what the shape looks like. And in physics, a simple harmonic motion model is also a model that's been used in many, many different places. um, um, even for simple harmonic motion, like when we use it to describe the electric signal that we use, it's also the sinusoidal wave shaped signal that looks just like how when you do a simple harmonic motion of a spring with something attached to the end, go back and forth, the same as if you have a pendulum going back and forth, and it's amazing that we are able to describe all those different type of motion using this simple harmonic motion model. So one way to make a simple harmonic motion is to, for example, attach a mass to a spring, right? You can say you compress the mass by amplitude A, and you push the spring and you let go. So what will happen is this mass will oscillate back and forth in between these 2 points, negative A to A, right? Okay, so this is a checkpoint question you have already done. We have a mass on a spring moves with the simple harmonic motion as shown. What is the acceleration of the mass being most positive? Okay. All right, so we have defined a positive direction that is to the right is a positive x, right? So in which way the acceleration being most positive? There are 3 points it's asking us. So let's look at these 3 points one by one. When the mass is at negative A, we want to know the acceleration. So that means we need to know which way the force is pointing at. So there is a force from the spring, right? The mass has gravity and normal force, but these two are canceled out in the y direction. So the acceleration is coming from the spring. So in which way do you think the spring is pushing on the mass at this point? Is the spring pulling the mass to the left, or is the spring pushing the mass to the right? Is it left or right? What do you think?
To the right.
To the right, because you're compressing the spring, right? You're compressing to the left, so it's going to push you to the right. So that one we know. Also, according to Hooke's law, right? You know that your force is always negative of your displacement. So this one is the force is to the right, so acceleration is to the right. And to the right is positive. Now, what about point A? What if mass now is at this location? Which way would the spring exert a force on M? Left or right? Here.
To the left.
To the left, because the spring is now pulling you back. So this one will be to the left. You can see that is in the negative direction. So that's most negative. This one would be most positive. This one most negative. What happens when mass is right in the middle? What about the force or the acceleration on mass M when mass is right in the middle? There is no acceleration. Very good, because you can see here is the equilibrium position. At that point is when the spring is neither stretched or compressed, is a relaxed spring. So there is no force if the spring is relaxed. So here is no acceleration. Okay, so the answer would be A. Now this slide has to do with derivation because students were wondering how do we get the simple harmonic equation to describe the motion of the M? Is there from Newton's second law? So let's do this derivation together. So again, this is the spring and the mass simple harmonic oscillation that you were just seeing. Okay, we wanted to be able to derive the position of the mass M as a function of time. So we're going to use Newton's second law. Just a second. Newton's second law to describe the motion of the mass, F equals ma. And you know the force is a spring force, right? So the spring force is negative kx. Okay, x is how much the spring is being compressed or it's being stretched. And we have located the x equals 0 to be when the spring is at a relaxed state. So you can see that to the right, is a positive x, meaning that your force is to the left. Now, if the mass is to the left, which means the spring is compressed and your force is to the right. Okay, so that negative kx describes the force in relationship to the location of the mass. Okay, so this is here x means the position of the mass. M times acceleration. Now, acceleration can be written in terms of the second derivative of x with respect to t, right? Because acceleration is dv dt and v is dx dt, right? So acceleration is the second derivative of x with respect to t. So this is a differential equation. Negative k over m x. Now we can let omega squared to be k over m, and this becomes something like this. Oh, sorry, omega squared. Okay, so with our knowledge with differential equation, of course, it is not required in this class. You know how to solve it. But generally in the process of solving these equations is you will have a book about differential equation, or you'll have to refer to some materials to see, okay, for this type of equation, what kind of general solution does it have? Or you can always, as long as you get a solution and it satisfies this equation, then you have found your solution. No matter if you had guessed it or if someone told you, as long as you can show that this is indeed a solution. So for example, I claim this is a solution to the problem, to the differential equation you were looking at. All you need to do is plug this in. You plug this in on the left-hand side, you get negative a omega sine omega t plus phi. The second derivative, you will get this. And you show it is indeed negative omega squared times x, right? So it's shown to be an actual solution. Okay, so this is the general solution that describe the position of the mass as a function of time. It's a sinusoidal wave. And we call this type of motion to be a simple harmonic motion. You can see we have some constants, right? We defined the constant omega, which has to do with the spring constant and the mass m. But we don't know what a is and we don't know phi is. So to define those constants, you need to know some initial conditions of your physical setup. So what are the initial conditions? Well, initially, you can say at t equals 0, the initial position of the mass could be at a maximum distance d, which means that at initial t equals 0, you have dragged the mass to a distance d away from the origin where x equals 0. And at that moment, you said, let go and let's observe its position. You start from that moment, you start taking data. So that's your initial conditions, okay? And also velocity at that moment is you just let go. So at that moment, you don't have any speed yet. The velocity is 0. So these are your initial conditions. Using these conditions, you can find out what the constants are. So let's plug in t equals 0. Let's plug in 0. Okay, so we get a cosine phi is equal to d, right? So because x at t equals 0 is a cosine omega times 0 plus phi is equal to a cosine phi plus d. So to make this equal, you can see that you need phi to be 0, so that cosine phi could be 1. And you need the a to be the maximum distance d. So we call the a to be the amplitude of the oscillation, because that's how far you can go to each side. You cannot go further than you were given the distance to begin with, right? So if I drag for 10 centimeters and let go, the second time to come back is not going to go beyond 10 centimeters, right? It's going to be at most which is 10 centimeters without friction. So that's the amplitude of the oscillation. Okay, we can also, so we can see that with these two, we can figure out that x as a function of t is d cosine omega t. We know these constants. Of course, it also satisfies the initial condition for your velocity. You can do a double check. Is velocity is negative d omega sine omega t, and at t equals 0, it is 0. So it is indeed satisfied the initial conditions, and this is the correct result to describe the position of the mass as a function of time, given the initial condition that you have dragged it for d, distance d, and you let go, it will just start oscillating back and forth, back and forth. So this is the result we just derived, right? Omega would be describing some intrinsic feature of your oscillator. Here it has to do with how strong your spring is and how much mass your mass M has. Now you can see that just like how you find out the amplitude for D for your position, you can find your maximum value for your velocity. And so it's going back and forth, back and forth. Where do you think the mass will be experience the largest speed? So it will be at 0 or negative d. I'm sorry?
At x equals 0?
At x equals 0, right in the middle. Very good. Now we know this, you can see from the math, you can tell, also from previously when we did conservation of energy, right? Because right in the middle, all the energy goes to kinetic energy. At point D, all the energy is stored in terms of the elastic potential energy, also with negative D. Right in the middle is where you have no potential energy and all of that going to its speed. So it's going to be the fastest speed is occurred at x equals 0. So that is the maximum value. You can see this expression is going to be omega d. That's the maximum value. Because sine of something, the maximum value of sine something is 1, right? The maximum value of cosine something is also 1. So the maximum acceleration is omega squared times d. The maximum speed is omega d. So these two you can get from the simple harmonic motion equation. You can also get this for conservation of energy. If you have set up your energy equations, you can solve from V max to be omega d. You can do that later if you wanted to confirm that. So you can see that not only the position time graph is a sinusoidal wave, is a cosine function, the velocity and acceleration is also a sinusoidal function. And omega d is a maximum value here, and omega squared d is a maximum value for your acceleration. Okay. Another thing I wanted to talk about is to see the relationship between circular motion versus the simple harmonic motion, and why they are described by the same mathematical expression. So if we consider a mass undergoing a circular motion, so showing right here, right, is going in a circular motion with a angular velocity omega, and there are some initial conditions. So we say, okay, at t equals 0, the mass is at an angle phi above the x-axis. So starting there, we call it t equals 0, and it's going in the constant velocity omega. So we're saying that this is very similar to this in terms of the x position of the motion. So if we look at the x, right, this is x. How do you calculate the x? So x at this location right now, at t equals 0, x at that location is r cosine phi. You can see, right? R cosine phi. Now, at some time had passed by, after some time, let's draw. After some time, the displacement of the mass would be omega t, because omega is angular velocity. Angular velocity times time is your angular position, is how much degrees you have passed by. So that is increase the angle by omega t. So at that location, you can see that the x position of the mass as a function of time is going to be r cosine of the new angle. New angle is the original angle plus the how much your mass have swept by. That's omega t, right? So that is x. The function of time is r cosine phi plus omega t. And that looks just like the motion of the mass on the spring, right? The difference is okay, now the amplitude is r, amplitude there is a or d as we called it, and you have an omega t there and you have omega t here. You have a phi. Phi is your initial position, describe your initial position, and oftentimes we call it the phase of the oscillation. Okay. So omega here is the angular velocity for circular motion. And omega there is related to the spring constant and the mass of the of the object. Okay, so that's why you can see there is a mapping onto the position of the object. Whether it's doing circular motion, the x position, just like how it's doing a back and forth oscillation when it's attached to a spring. So that's why we say the simple harmonic motion model is very useful, because you can see a circular motion, you can find the use in describing the motion of the object, and for an object on the spring, you can find the use to use this model. So it's very useful. All right. Oftentimes, you will see that it's not a perfect cosine shape, right? The one that we had just talked about is a cosine omega t plus phi. So it's not a perfect cosine because there's a phase. So these two different drawings has a phase difference and phase difference of phi. So if you were giving these two graphs, right, you know that one of them is cosine omega t and the other one has to be the other a cosine omega t plus phi. So which one is a cosine omega t, the red one or the blue one? Which one is a perfect cosine function?
The red one?
Yeah, the red one, yes, because at t equals 0, cosine of something is 1. So this one obviously is a cosine function. Now the other one gotta be cosine omega t plus phi. Okay, so how do we draw? How do we know how to draw the phase difference? We know there are, it's like the whole wave is being shifted. But how do we know to shift it to the left or do we shift it to the right? So there's a way to figure that out. So we're going to say, okay, let's look at the peak value. For the cosine one, we know that it peaks at t equals 0. Using that as a reference, let's see how, which one, at what time this function peaks, okay? So when it peaks is cosine omega t plus phi is 1, that is the peak, which means to get that you need omega t plus phi to be 0, right? Because cosine of 0 is 1. So from that you can calculate then the omega t is equal to negative phi. So t is negative phi over omega, okay? And that shows a time, so that is a little bit earlier, occurred a little bit earlier than the red one. So we are saying if it's cosine omega t plus phi, we call this wave to be leading the cosine omega t. So this one leading the other one. If I draw another one, be something like this. So this green one if you were to write out the expression for the green one, what would you do? The green one is A cosine omega t, and what else goes in there? So it's when I take the red one and shift it to the right, instead of shift it to the left, I shift it to the right, and I got this green wave. And how do I write the math expression for the green wave?
A cosine omega t minus phi.
Minus phi, very good. You can see that this one tells me it will peak at a time that happened after 0, not at 0, but phi over omega. So it peaked a little bit later than the red wave. So this one you can say it's a lagging. So this one is lagging the other function. Okay. All right. So knowing that, we can begin to process this checkpoint question. What I want to say is we can quote a direct result, and to answer this question, that's plenty, that's enough for as far as we care here. But I do want to show a little bit more the process of how we get a superposition of two waves combined together. So if you superpose two sinusoidal curves onto each other and add it together, what kind of plot would you get, right? Would you get something that doesn't look like a sine wave at all? Or do you look like something very similar as before? Or do you get another sine wave, but the frequency seems to have been shrunk down? So C. So I want to tell you that the result is B, because when you superpose two sinusoidal waves with equal frequencies, then they give you another sinusoidal wave with the same frequency, but they may have different amplitude and phase, but the frequency is the same. Now, what do I mean by frequency? So how can we tell frequency from a graph? So I don't know if this helps. If you take a rope, right? And on one end, you start shaking it up and down, up and down, up and down, up and down. So you can see on this side, you are kind of doing what the mass on the spring is doing. So it's just back and forth, back and forth, back and forth. Instead of doing back and forth, you're shaking it up and down, up and down, up and down. So what happens to this rope is going to have this wave shape like a sinusoidal wave, okay? And if you shake it really, really fast, versus if you shake it really, really small, you have two different frequencies, right? So frequency F is 1 over T. T is the period, is how much time it takes to go up and down and back to here again. So that's one complete oscillation. You're back to where you started. So how much time that takes is the period. 1 over that is the frequency. So you can think of frequency, I would say in 1 second, I have to go back and down 2 times. So that is a frequency. If I have a really large frequency, meaning that in 1 second, I go up and down, up and down, up and down, back to where I was 10 times. So that's extremely fast, right? If I go really, really small, I have a small frequency. So you can see that we can tell by looking at the graph. For example, one complete oscillation, this is the time. Okay, so you can see this is the time it takes. Now, if something has a different frequency, the time will be different, right? Frequency is different, which means time is different. So something like this would have a bigger period, meaning that it takes longer for it to go one around, will have a smaller frequency. Something that is like this will have a smaller time, a bigger frequency. So it takes half a second for me to go one oscillation. So in 1 second, I'm able to complete 2 oscillations, right? That is a bigger frequency if I were able only to complete 1 oscillation. Okay, so you can see how big or how narrow this wave is, describe the frequency, or you can say describe the period, but we like to just call it the frequency. So that's also when we do, we have electronic signals that oftentimes we superpose two sinusoidal waves signal together, and you can get a combined signal that is also sinusoidal. As far as this question, I think it's good to know that when you combine two waves with equal frequency, you always get the sinusoidal wave, just with the same frequency but different amplitude and phase. But I also want to show maybe just a little bit more of the math of why this is the case. Okay, so you can see the superposition of these two waves. We can say this is our cosine wave. Now the other one, we can view this as a cosine plus phi wave because we have just talked about these two different types of waves. So you can see, okay, when I superpose, it's like using a cosine omega t plus a cosine omega t plus phi. And what does that become? You can always go back and rely on your math to see what is the superposition looks like. So we can figure that out using this trig identity, okay? Cosine of something plus cosine of b, or something else is 2 cosine a plus b over 2, cosine a minus b over 2. Now in this case, we have a cosine omega t plus a cosine omega t plus phi, right? They have the same amplitude. So it's a cosine a plus cosine of b. So if you let omega t to be a, omega t plus phi to be b, you can use this trig identity and found out the final result will look like this. So what is this? This is a cosine wave. So it's still a cosine wave with the same frequency, yes. What's in front of your t is your frequency, and that is still omega. Same frequency, but different amplitude. Yes, different amplitude. I got a 2 cosine negative phi over 2. So this will be, so my amplitude before is what? Is A. What is amplitude? Is how far the wave can go. So the peak value is A. That's when omega t is 0 and cosine omega t is 1. It's your peak value. But now your new amplitude is A times this extra stuff, 2 cosine phi over 2. This is just a number, right? It's just a constant. Phi is a number, so cosine of that is a number. Let's just give you a new amplitude. And also got a new phase. This phase is phi over 2. Whereas before, this guy has a 0 phase, this guy had a phase of phi. So when they superpose, they get a new phase. Okay, so you can see that you can also use math to figure out that B was the correct answer. All right, so now let's look at a question that you are going to answer. We have mass oscillates up and down on the spring. So it's now going up and down. I think it's easier to visualize, to combine this up and down with our wave up and down. The position as a function of time is described by a sinusoidal wave that looks like this. At which of the points does the mass have positive velocity and negative acceleration? Okay. So I want to give you a little bit hint to answer the question. You might be able to simply just look at the graph and you can tell. You can think of, okay, a mass going up and down. So when my mass is up here, right, in this location, my acceleration is always been pulling down, right? When my mass is down, my acceleration is pulling it up. So kind of that can give you an idea of which way the acceleration is pointing at. Also, to figure out the velocity, right, you want to see the slope of your position graph gives you velocity, right? So which one has a positive slope will give you a positive velocity. A negative slope will give you a negative velocity. Okay, so take some time to discuss this, maybe a few minutes, And after your discussion, we can come back to vote on this. Take a screenshot and I'll open up our breakout rooms. Okay. All right, 10 more seconds. If you haven't voted already, we'll wait for 10 more seconds. Okay, it seems like it's got a little bit stuck. Okay. Okay, it's really, I think Zoom is a little bit sluggish right now. Let me attempt to close it. I don't know if I could because my mouse is like doing this right now. Looks like it's it is just going really slow. Okay, all right, let's take a look at the results, okay? This is our result. All right, positive velocity and negative acceleration. Let's figure out the velocity. We want to say the slope represent positive or negative velocity. Remember how we draw the slope? Given a position time graph, to get the slope, what do we do? So how do I draw the slope here? Are you guys able to hear me?
Yeah, I really laggy apparently.
Okay, you were cutting off a little. Was I also cutting off? Was my voice cutting off?
Yeah, I think you're cutting out, Professor.
Okay. All right. Maybe now is better. Is now better? Okay, so the tangent of the point. Yes, thank you, Eric. To do the slope, you want to draw a tangential right here to show the slope. Okay, and then this is not updating. Okay, and then point B and point C. So you can see both B and C give you a positive slope, right? Whereas A give you negative slope. So B and C will have positive velocities. So B velocity larger than 0, C velocity larger than less than 0. The next thing to look at is to look at the acceleration. So you can see that wherever you have a positive position, you have a negative acceleration, right? If you have a positive position, your force is always opposite to your displacement. If you're above the 0, your force will be dragging you down. You have a positive position, you have a negative acceleration. So here at point A, you have a negative acceleration. You have a negative acceleration because these 2 points are both above the 0 point. But point B, you're going to have a positive acceleration, right? So the question is asking which one has a positive velocity but negative acceleration.